Hello everyone from Math 2200, Discrete Mathematics. Professor Wenson here again with a video on your ZyBooks Section 6.1, an Introduction to Binary Relations. Okay, so this entire chapter 6 is on these things called relations, and also things called directed graphs or digraphs. And we'll see examples of these in section 6.1, an introduction to them. Now, if you recall a function, right, a function from one set, a domain set onto a target set, it was just a subset of the Cartesian product of the domain set with the target set. Well, a relation is even more general. A function is just a special kind of relation. So in a relation, you have a domain set, you have a target set, just like in a function, but there's not that restriction that every element of the domain set has to map to exactly one element in the target set. That is no longer a restriction. Right? And that's it. It's really that general. Right? It's much more general than a function. Right? So we'll be introduced to them and show you some notation and all that. All right, so a binary relation is a way of expressing a relationship between two sets, as I mentioned. Mathematically, a binary relation between two sets, A and B, is a subset R of A cross B, right? So just like a function was. A function was also a subset of the Cartesian product of two sets, right? So same with a relation. But a relation is more general, doesn't have the restrictions that a function has. The term binary refers to the fact that the relation is a subset of the Cartesian product of two sets. The two sets A and B may or may not be the same set, may or may not be equal. For an element A belonging to set A and an element B belonging to set B, the fact that the ordered pair A comma B belongs to relation R is denoted by ARB. A is related to B. Right? It depends. If the relation is called R, they'd say ARB. If the relation is called something else, then they'll use that letter instead of R. Suppose, for example, that S is the set of students at a university, and C is the set of classes offered by the university. The relation called E, right, instead of R, between S and C indicates whether a student is enrolled in a given class. So if they said SEC, that would mean that student S is enrolled in class C. So a student can be enrolled in more than one class, and a class can have more than one student enrolled in it. If a student S is not currently taking any classes, then there is no C such that SEC. Right? That means the student's not enrolled in any classes. Similarly, if a course C is not currently offered by the university, then there is no S such that SEC. Right? But again, there's no restriction like with a function. Remember, a function, every element of one set, the domain set, had to map to exactly one element in this other set, the target set. That is not happening here. There is not that restriction here. Relations can also be defined on infinite sets. For example, we can define a relation called C between the real numbers and the integers to be the following. X is related to y, xcy, if the absolute value of x minus y is less than or equal to 1. Thus, that is xcy if the distance between real number x and integer y is at most 1. If two sets A and B are finite, then a binary relation called R between A and B can be represented by a list of ordered pairs. Remember, every relation is just a subset of the cross product, right? Like it was said in the first paragraph. A relation can also be specified in a more graphical way in an arrow diagram, which you've seen for functions, is now coming back here for relations. The elements of set A listed on the left, the elements of set B listed on the right, and there is an arrow from A to B if A is related to B, right? If A are B. All right, so they give this example here. And you can play the animation, I'll just read it off. So I've got this set of people, Sue, Harry, and Sam. You have this set of files, file A, B, C, and D. And the relation A, they say P, A, F. A person is related to a file if person P has access to file F. And here's an arrow diagram for this. You have the people on the left, the files on the right, and then the arrows. So Sue has access to file B, file C, and file D. So notice again, already you're seeing it doesn't have to be a function anymore. Right? A relation is much more general. So this relation A is set A is a set of ordered pairs. Sue, comma, file B, Sue, comma, file C, Sue, comma, file D. Right? Because I got arrows. Those relationships. Harry has access to file A. Harry also has access to file D. So then in the set of ordered pairs, you have Harry, comma, file A, Harry, comma, file D. And Sam doesn't have access to any of the files. So notice there are no ordered pairs with Sam in the first coordinate. And this is perfectly valid. This is a totally valid relation. Again, a relation is not every relation is a function. But some relations are functions. A function is a very, very specific kind of relation. Okay. Now you could also, there are lots, all right, so there are going to be lots of ways to represent relations. You can write it out in words, like they did here. Right, write it out in words, the description. Come on. You can make an arrow diagram. You can write it as a set of ordered pairs. And one other way we're going to see to represent a relation between two sets is by using a matrix. Right, a matrix representation. So a matrix representation of relation R between sets A and B is a rectangular array of numbers with the cardinality of A rows. So however many elements A has, that's how many rows the matrix will have. And however many elements B has, that's how many columns the matrix will have. And each row corresponds to an element of A. Each column corresponds to an element of set B. Now for an element of A called little a and an element little b of set B, there is a 1 in row A, column B, if A is related to B, if A, comma B is in the relation. And if it's not in the relation, they put a 0 to indicate that they're not related. So back in this picture, same relation they're doing down here. So Sue has access to file B, file C, and file D. Harry has access to file A and file D. And Sam doesn't have access to any of the files. See, they create this 3-row, 4-column matrix. Rows are horizontal, columns are vertical. And each row, corresponds to a different person. The Sue row, the Harry row, the Sam row. Each column corresponds to a different file. File A, B, C, and D. And Sue, right? Sue does not have access to file A. So the Sue row, file A column, see how that entry is a 0? that just means Sue does not have access to file A. But Sue does have access to file B, so you see a 1 there. Sue has access to file C, you see a 1 again. And Sue has access to file D, you see a 1 again. And then the Harry row, Harry has access to file A, you see a 1. He doesn't have access to file B or C, so you're seeing zeros there. And then he has access to file D, so you're seeing a 1 again. So basically for any ordered pair you come across in the relation, you're going to see a 1. And then Sam has no access to any of the files, so zeros for all. And you get this 3 by 4 matrix, 3 row, 4 column matrix representing this relation. So now you have a matrix, you have an arrow diagram, set of ordered pairs, a description, maybe an equation, if it's like between sets of numbers, lots of different ways to represent a relationship between two sets. Okay, so now they give us an activity here. So suppose set A is just a set with 2 elements, 2 and 3. They're asking us to define the relation R between set A and the positive integers. So this is like the domain set, and this is like the target set. All right, that's a set of positive integers. And the relation is described this way. Element A from set A is related to element X from the positive integers if X is an integer multiple of A. So I'm going to go a piece of paper here. I'm going to draw some stuff. All right, we're going to represent this in a couple different ways. Okay, so here's what we're told. All right, this capital R is a relation between set A, which only has the elements 2 and 3, and this infinite set, the set of positive integers. And A is related to X, if X is an integer multiple of A. Now, I could start making, now this set is infinite, Z plus is infinite, so I can't make a complete arrow diagram. One of the set, I can't possibly write all the elements of the positive integers, but I'll start off by trying to make one. Over here I have the elements of set A, kind of like the domain of a function, but again, this is not a function. So you got the element 2 and the element 3. And then over on this side, I got the elements of the positive integers. Now again, there's infinitely many of these. I mean, there's no way I'm going to write them all. So you got 1, 2, 3, 4, 5, 6, and so on, right? It goes on forever. Now they're telling us the relationship, right? They're saying there should be an arrow from an element of A to an element of Z plus. If the element of if the integer in Z plus is an integer multiple of A, so is 1 a multiple of 2? No. Is 2 a multiple of 2? Yes. So 2 maps to 2. All right, another way I could write that is 2R2. And what that means is that the ordered pair 2, 2 belongs to this relation called R. All right, these mean the same thing. All right, is 3 a multiple of 2? No, but 3 is a multiple of 3. So I've got an arrow from 3 to 3. All right. So 3R3. In other words, the ordered pair 3, 3 belongs to this relation R. Is 4 a multiple of 2? Yeah. 4 is a multiple of 2. Alright, so that means 2R4. Alright, separate these. So that means that 2 is related to 4. In other words, the ordered pair 2, 4 belongs to this relation R. I could do this forever. Is 4 a multiple of 3? No. Is 5 a multiple of 2? No. Is 5 a multiple of 3? No. Is 6 a multiple of 2? Yes. So I have an arrow from 2 to 6. Is 6 a multiple of 3? Yes. So I also have an arrow from 3 to 6. And I can keep going, right? 2 would map to all the even, right? 2 would map to 2, 4, 6, 8, 10, and so on. 3 would map to all the multiples of 3. 3, 6, 9, 12, 14, 15, and so on. Right? And if I wanted to write this as like a set of ordered pairs, again, there's an infinite number here, but so this relation R, remember, it would have, it has the ordered pair 2, 2. It has the ordered pair 2, 4. The ordered pair 2, 6. The ordered pair 2, 8. Dot, dot, dot. Also, 3, 3. 3, 6. 3, 9. 3, 12. Dot, dot, dot. It's got all these ordered pairs, infinitely many. And if I wanted to try, I could also try making a matrix. Another way to write this also. Another way to write this. I could write it in that set builder notation. Maybe this is all the ordered pairs, A, X, such that X equals, K times A for some integer K, right? Because that's what's being explained to us up there. Right? X is an integer multiple of A, right? For some integer K, right? So there would be a way to describe this same set in set builder notation. Oh yeah, I guess also and A belongs to A, right? And A belongs to A, and X belongs to Z plus, right? That kind of stuff. But that's kind of assumed, right? And notice, right, this is a subset of A cross Z plus, right? Every first coordinate of these ordered pairs is from A. Every second coordinate of these ordered pairs is some positive integer. And then I could also try, now this is impossible, but because one of the sets is infinite, but I could also, if I were making a matrix for this, I'd have 2 rows, right? 2 rows. One corresponding to the element of 2, one corresponding to the element of 3, right? The rows are from set A, and then the columns 1, 2, 3, 4, 5, 6, 7, 8, dot, dot, dot. It's impossible to make the whole matrix. It would be an infinitely large matrix because the number of columns would be infinite. But is 2 related to 1? No, we didn't see an arrow. 2 is related to 2 though, so I put a 1. Then not 3, and 2 was related to 4. Not 5, 2 was related to 6. Not 7, 2 was related to 8, and so on, right? So it would continue 0, 1, 0, 1, 0, 1 forever. And then the 3 row, 3 was not related to 1, not related to 2, but 3 is a multiple of 3, so it is, 3 had an arrow going to 3. Not 4, not 5, but yes to 6, so a 1 there. Not 7, not 8, and yes to 9. So it would go 0, 0, 1, 0, 0, 1, 0, 0, 1, the whole way down, forever. Okay. All right. So just again, many, many ways to represent a relation between 2 sets. So is 3 related to 8? Nope. Right? 8 is not a multiple of 3. So that's a false statement. Right? 4 related to 8? No. No. remember, in this relation, the first element has to come from set A. Is 4 in set A? No, it is not. So you might think, oh, 8 is a multiple of 4. Yeah, but is it in this relation between these two sets? No, it is not. Because again, the first element has to be either 2 or 3. So this is also false. So be careful. There is an element of A such that A relates to 7. Is 7 a multiple of 2 or 3? No, it is not. So that's also false. And I'll let you look at the last two. All right, you can read the example there. All right, now, it is possible to have a relation between two sets A and B in which they're equal. All right. So like my example, the last example was from, the set with 2 and 3 in it to the set with all positive integers. Those are clearly not the same set. Or that set with people to this set with files. They're clearly not the same set. But what if we do have two sets that are exactly the same? So if that's the case, they call that a binary relation on a set A. So that's from set A to set A again. And it's a subset of A cross A, or A squared. And the set A is called the domain of the binary relation. Now, for these, the arrow diagrams change a bit. They're going to be drawn as what are called directed graphs or digraphs. We'll see that in a little bit. And I'll show you here with this. So define the relation R on the positive integers. So this, now when they say again, relation on a set, that means both sets, the domain set and the target set, both sets are the positive integers. As follows. So one positive integer is related to another positive integer if A and B are relatively prime. That means the only positive integer that evenly divides both A and B is the number 1, right? The largest number that goes into both of them is 1. All right, so again, I'm going to go to a piece of paper and I'm going to start representing this relation in multiple ways. All right. So here, R is a relation on the positive integers, and this is what they gave us. They say that one positive integer is related to another one if they are relatively prime, meaning the greatest common divisor of the two numbers is 1. Right? The largest number that goes into both of them is 1. Now, when you have a relation on a set, meaning that's this relation R is going to be a subset of Z plus cross Z plus. It's going to be made up of ordered pairs where the first element and the second element, the second component of every ordered pair is going to be some positive integer. When these are the same set, all right, instead of an arrow diagram, now it'll still look like an arrow diagram, I'll still be using arrows, but if this is the case, if these two are the same set, instead of an arrow diagram, we draw something that's called a directed graph. And we'll learn a lot more about these in later sections in this chapter. A directed graph. A shorter way of saying this is digraph, directed graph. Right. Because, these are the same set, so you don't need to it would be kind of redundant to copy the same set twice. So what they do is you just write the set once. So here is the set of the positive. Now I know there's infinitely many, but I write the positive integers out. There's one. I just write them all over the place. Try to evenly space them because I'm not doing a typical arrow diagram here. I'm not going to repeat the set twice. There's no need. I just write the set once. So there's 1, 2, 3, 4, 5. Just put them, space them out. 7, 8, 9, 10, and dot 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 dot. There's infinitely many. I can't possibly write them all. And then if one, if an element is related to another element, if it satisfies this, then I draw an arrow between them. So like, is 1 related to 1? Yes. The largest number that goes into both 1 and 1 is 1. So I do this. Little self loop. 1 is related to itself. We have a 1 is related to 1. Or in other words, the ordered pair 1, 1 belongs to this relation. And really 1 would be related to every single integer. Because the largest number that goes into 1 and any other integer, any other positive integer, is 1. So 1 is related to itself. 1 is also related to 2. 1 is also related to 3. 1 is also related to 4. 1 is also related to 5. And 6. And 7. And 8. And 9. And 10. I mean, maybe I shouldn't have put so many on here. And 11. And 12. And blah, blah, blah. 1 is related to every other integer. So I'll put some of those down. So 1, 2 belongs to this relation. In other words, 1 is related to 2. Now, you see how the other way around would work as well? If I just switch the order, yeah, 1's related to 2, but isn't 2 also related to 1? Right? 2 and 1, the largest number that goes into them is 1, so that belongs to the relation as well. So the ordered pair 1, 2 belongs to the relation, but so does 2, 1. Right? So not only does 1 have an arrow going to 2, but 2 also has an arrow going right back to 1. Same thing for 3. So this is going to be ugly. Same thing for 4, right back to 1. Same thing for 5, right back to 1. For 6, for 7, for 8, for 9, for 10. This is hideous, right? This is hideous. And we're not going to be doing this, a digraph for infinite sets like this, because you could see how hairy it can get depending on the relation. Right. So that's just one swift example. Now 2 and 3 are related, right? Because their greatest common divisor is 1. 2 and 4 are not related, because their greatest common divisor is 2. 2 and 5 would be. 2 and 6 are not. 2 and 7 would be, right? So you could draw all sorts of arrows on this, and it would be hideous. It would be very, very difficult to look at. And you could also try making a matrix, a set of ordered pairs, right? But again, because there's infinitely many numbers here, those wouldn't be very nice to write. All right, so let's go back. So is 8 related to 12? Now both of these are positive integers. That's fine. But is their greatest common divisor 1? Are they relatively prime? No. Their greatest common divisor is 4, not 1. So this is a false statement. 8 is not related to 12. How about 21 and 20? They're both positive integers. Great. The largest number that goes into both of these is 1. Right? This is true. They are relatively prime. Is there a number other than 1? Other than 1? That's related to itself, right? We said that 1 was related to 1, but is 2 related to 2? No, the greatest common divisor is 2. Is 3 related to 3? No, their greatest common divisor is 3. Anything other than 1, the greatest common divisor of it with itself would be itself, which is not 1. So there's a number other than 1 that's related to itself? No, there isn't. And is there a number that's related to 7? Yeah. 6 is related to 7. 5 is related to 7. 4 is related to 7. 1 is related to 7. So definitely. There's definitely numbers that are relatively prime with the number 7. Just not like 7 or 14. And none of the multiples of 7 would be good. But anything that's not a multiple of 7 should be fine. Alright, and as I mentioned, we're not drawing the typical arrow diagram. Alright, we're drawing what's called a directed graph, a digraph, for these relations on a single set. Right, from where the set, the domain set and target set are the same set. So an arrow diagram for a relation R on a finite set A requires only one copy of the elements of A, right? No need to write it twice like I was saying. There is an arrow from A to B if A is related to B. An element can have arrows heading into it and arrows that head out of it. An element that is related to itself is indicated by an arrow called a self loop. And that's exactly like I drew in the previous picture where I had 1 was related to itself, right? Drew an arrow right back to itself. A self loop leaves the element and then turns around to point to itself again, like they do with D down here. Okay, so here's an example, right? Say set A, the domain set, and the target set are this set with elements A, B, C, D, and E. R is some relation on A, so R is a subset of A cross A. And here's R. It's got A comma B, B comma C, E comma C, C comma E, D comma A, D comma D. So A is related to B is related to C, E is related to C is related to E, D is related to A, and D is related to itself. And see, they draw just this one copy of set A. They don't have set A on the left or set A on the right. They just draw one copy. A, B, C, D, and E dots. And notice how they kind of spread them out a bit, right, instead of putting them in a line. You could put them in a line if you want. I mean, it'll just kind of make the drawing uglier, kind of like my last drawing. And then you see A is related to B, so I've got an arrow here from A to B. B is related to C, so you got an arrow here from B to C. E is related to C, so I got an arrow from E to C. C is also related to E, so you got an arrow from C right back to E. D is related to A, so I got an arrow from D to A, see that? And then D is related to itself, so you see this self loop, D to D. All right. And you can watch the animation if you want on that. All right. And then again, you can make a little matrix for this, and I'll make a matrix. All right, so look at this example here, and I think, yeah, so I'll do this on paper. I'll write this relation up and show you an arrow, the arrow diagram called a directed graph, and a matrix representation for this relation. Okay, so we have this set A with elements 1, 2, 3, and 4, and then we have a relation here called R with these ordered pairs where, again, this is a subset of A cross A, or A squared. Every first coordinate is from A. Every second coordinate is from A. All right. Now because this relation is a relation on a single set, right? The two sets here are the same. Instead of making an arrow diagram like usual, from 1, 2, 3, 4 to 1, 2, 3, 4 again, that's kind of redundant, right? Why copy it twice? So again, we make this thing called a digraph. All right. So I just copy this around. I'll spread them out. Now again, you can draw them in a straight line. That's fine. Wouldn't be wrong. It's just your arrows might get a little ugly. So I'll spread them out. 1, 2, 3, 4. So there's element 1, element 2, element 3, element 4. There's set A written out once, right? There's no need to copy it twice. And look at the relation. Look at what ordered pairs are in this relation. What are the relationships from A to A? We see that 1, 2. 1 is related to 2. So I draw an arrow. 1 to 2. 1 comma 3. 1 is also related to element 3, so from 1 to 3. 2 is related to itself. So I have one of those self loops. Right? 2 goes out and then comes right back, points at itself. 2 is also related to 3, so I have an arrow from 2 to 3. 3 is related to 4, so an arrow from 3 to 4. And finally, 4 is also related to 3, so I have an arrow from 4 going right back to 3, like that. And there's a directed graph, or a digraph, for this relation on set A. And I could also represent this with that matrix representation that was mentioned. So I'm going to have the elements of set A on the left, 1, 2, 3, 4, represent the rows. So I'll make a little bracket here. So it's going to have 4 rows. And then the target set, the set where all the second components are coming from, is also set A. So 1, 2, 3, 4. So I got 4 columns as well. So a nice square matrix where the numbers of rows and columns are the same. And then, is 1 related to 1? Nope. So I put a 0 there. Is 1 related to 2? Yeah, 1 comma 2. Got an arrow going from 1 to 2, so yes, put a number 1 there. Is there an arrow from 1 to 3? Is 1 related to 3? Yes. So a 1 there. Is there an arrow from 1 to 4? No, there's no ordered pair 1 comma 4, so I put a 0. It's really that simple. All right. So is 2 related to 1? No. Is 2 related to 2? Yeah, I got the ordered pair 2 comma 2, yes. 2 is related to 3, 1 there. And is there an ordered pair 2 comma 4? Is there an arrow from 2 to 4? No. Now for the row for 3. Is 3 related to 1? Nope. Is 3 related to 2? Nope. The only one 3 is related to is 4. There's only an arrow coming off of 3 to 4, so I got 0, 0, 0, and then 1. And finally for the row for 4, 4 to 1? Nope. 4 to 2? Nope. 4 to 3? Yeah, there's 4 comma 3. And then from 4 to 4, no, there's no self loop on 4. And there's a matrix representation of the same relation. 3 different ways to picture the same relationships. All right, and so then looking at this, which pair is in the arrow diagram? All right, so now they're telling you, hey, so you saw my drawing. All right, I'll pull it up on the right corner of your screen here. There's my drawing. Look at their drawing. It says, which pair is in the arrow diagram, but not in the original, not in the set of ordered pairs, not in R, not in the relation. So let's see, which of these? See, they got 3 to 2. See, they got an arrow from 3 to 2. There's no ordered pair 3 to 2. So which pair is in the arrow diagram, but not in the relation? The ordered pair 3 comma 2, right? They want you to enter it as 3 comma A comma B, 3 comma 2. So let's check that and say it's correct. And that's in the arrow diagram, but not in the relation. Number 2, which pair is in the original relation, but not in the arrow diagram? Well, see, they have 4 to 3, right? See, they have 4 to 3, but they don't have 3 to 4. They don't have the arrow from 3 to 4, so I'd enter 3 comma 4. Which entry in the matrix is a 0, but should be a 1? And they want you to enter it in the form parentheses, row number, all right, so I'll show you how to enter this, right? So look it back up here. My matrix looks like this. 2, 2, right? See, their 2, 2 is wrong. Their second row, second column should be a 1, but it's a 0. So I put in parentheses 2 comma 2, right? They want row number comma column number in parentheses like that. And then which one's a 1 but should be a 0? Again, compare that to my matrix. Their second row, fourth column, 2 comma 4, is a 1 when it should be a 0. So again, hopefully pretty easy to see, hopefully pretty easy to go through. All right, then you have your additional exercises. You got some matrices here. They want you to give a set of ordered pairs. You got some digraphs. All right, some directed graphs on a set. Here you're asked to make an arrow diagram, right, or a directed graph. Well, actually, no. A and B here aren't the same set. A and B are not the same set. So you would make an actual arrow diagram. Yeah, here you could make a digraph because it's a relation on a single set, so you can make a directed graph here. So yeah, just pay attention. More arrow diagrams. Yeah, okay. So again, some of these, maybe all of them are on assignment 6. I would still, even if they're not all on the assignment, I would still recommend trying them all just to get more familiar with the material, get more practice. You can look at the solutions, to help guide you or check how you did. And I beg this of you every video, right? Don't look at the solutions right away. Try to work out the problems. Try to figure things out on your own before you look at the solutions. Because if you're just looking at the solutions and copying them, you're not really learning anything and you're wasting your time. So that's it for 6.1, this introduction to binary relations, right? Sets of ordered pairs, really. If you have any questions, of course, let me know. And thank you very much for watching.